to understand what makes a quandle, we come back to the idea of coloration, right? And the notion that if I have three colors to use, for example, then I can come up with this crossing relationship that can tell me, given two colors that I use at a crossing, how to determine the third, right? And so I think of a quandle as being like that box of colors that tells me what crayons I have, and then how, given two of those colors, I can compute the third. So if I have a three-coloration quandle, for example, that it would look like this, like 0, 1, and 2, and then the crossing operation tells me, given a 0, 1, or 2, and another one, how to compute the third one. So this is how I usually think of the picture of what a quandle is when it relates to coloration. But the fact is that a quandle we want to see as a more abstract object. We want to understand what its fundamental structure actually is. And to do that, we'll return to this idea that what we're really doing when we define any sort of crossing operation on oriented knots is we're telling how to relate the inbound and the bridge arc at a given crossing to the outbound. Right? And at a positive crossing and at a negative crossing, we know how to distinguish between those two now, and we know how to use notation. Right? X triangle Y is going to be the result of this underpass. X inverse triangle Y is the result of that underpass. Now, if we're going to define a structure using this operation, and we want that structure to be not invariant, then we want this triangle operator to be insensitive to the three Reidemeister moves that determine the equivalence of knot diagrams. Okay? So how do we guarantee, what properties does triangle have to have in order to make it a Reidemeister invariant? So for the three Reidemeister moves, let's suppose that I have a strand here that's colored the color X. Okay? And I don't have any crossings in this part of the strand, but if I apply the twist, the type 1 Reidemeister move to this strand, I'm going to have a new crossing where I didn't have one before. Okay? And at this new crossing, I'm still going to have these pieces of the arc are still going to be the same. They're still going to be colored red. They're going to be colored X, if you like. And then how do I then need to color this outbound strand, which just crossed under? Well, on the one hand, it's going to be the same as X triangle X. Because in this diagram, if I'm driving my car along X, I see my bridge traffic going from my left to my right as I cross under the bridge. So this is a positive crossing. That means that this color has to be X triangle X. On the other hand, this is the same arc as this arc up here, which already has the color X associated with it. So how are X triangle X and X related? They got to be equal. So the first property we need the quandle operation to satisfy is X triangle X is equal to X. Call that idempotency. I'll spell that word on the handout I'm going to give you in a second. It just means anytime we triangle something with itself, we always get the same thing back. This makes sense because valid coloration guarantees for us that anytime two of my colors at a crossing are the same, the third one has to be the same also. So X triangle X has to equal X. The second Reidemeister move, the poke, asks what happens if I have two strands that don't cross one another, and then I poke one of them over the other, or under, if you like. How am I then forced to color the remaining strands? Well, on the one hand, if I follow this arc under the bridge, I'm going to end up with a color that we're calling X triangle Y. Again, positive crossing because the bridge traffic is going from left to right. I'm arranging all these diagrams so that we always have positive crossings, by the way, so I'm going to stop belaboring that point. So we get X triangle Y on the other side. But then immediately we turn our car back around and we go cross back under the bridge that we were under. So I just lied to you because this crossing is now going to be a negative crossing. Because now as I drive my car southbound, my traffic is going from right to left on the bridge. So that will be an inverse crossing. So on the one hand, that color is going to be X triangle Y inverse triangle Y. On the other hand, that color has got to be the same as the color that it started with, which was the same color as we had over here, which was X. So this combination has to equal X for a quandle operation. In general, the existence of this inverse triangle operation just indicates that the triangle operation is an invertible operation. So as long as we can always undo a triangling by an element on the right, then that will satisfy our type 2 Reidemeister equivalence. The third one is even more interesting. So this one will have all positive crossings in it. But if I start with a crossing here and then a strand that goes under both of those crossing strands, if I start as x on the bottom and then when I cross under y, I become x triangle y. If I then cross under z, I become x triangle y, triangle z. So that's the color that I get at the top end of this strand here. I'll call it purple, x triangle y, triangle z. But if this is going to be Idempotency invariant, then I should get the same color on top after I take this whole strand and I move it from the left side of the crossing to the right side of the crossing, the slide in Idempotency colloquialism. So I'll just follow this strand through the spaghetti junction here again. Except this time, the first thing I'm crossing under is z. So I'm going to have x triangle z right there. And the next arc that I cross under is this one, but this arc has a color of y triangle z. And so at the end of the day, what I get here is x triangle z triangled with y triangle z. And the point is that that color that I get up here at the top is supposed to be the same as the color that I got up at the top here, because those are going to connect to the same parts of the knot diagram that we had before. And so the third property is that x triangle y triangle z has to be the same as x triangle z triangle y triangle z. What kind of property does this look like? Close. So associativity would... Yeah, this looks like a distributive property. What's the difference between this and the kinds of distributive properties that your algebra students know and love? Yeah.
Let's say add the middle.
Yeah, right. So what's different about this is that the operation inside the parentheses and the one outside the parentheses are the same operation, right? In standard algebra, in the algebra of rings, for example, multiplication on the outside, addition on the inside, different operations. Here, it's the same operation out as in. So instead of calling this a distributive property, we call it a self-distributive property. This is an operation which distributes over itself, which, you know, let's face it, a lot of algebra students want operations to distribute over themselves a lot, particularly things like multiplication, like x times y times z. Oh, I'll just jump the multiplication across the parentheses. Well, that doesn't work in general. But for quandle operations, it must work in order for the quandle that we define with this operation to be Idempotency invariant. And so what we say is that any set endowed with an operation that satisfies these three criteria is what we mean by a quandle. So it's like when we define a group as a set of elements along with an operation that satisfies bing, 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 bing. Right? Same idea. It's just that now we're putting different kinds of conditions on the operation compared to when we studied groups. So this is what a quandle is. And more to the point, the fundamental quandle of a knot. This is this thing which is going to be our complete invariant, capable of distinguishing anything about a knot except for its chirality, right? Except for its chiral opposite. The way to make the fundamental quandle of a knot is to use as the elements of the set all of the arcs in my knot diagram, and then also throw in all of the triangles of those arcs one with another. So throw in A1 triangle, A2, A1 triangle, A3. Throw in the triangles of those things with everything else. So everything which we can build out of these arcs combined with the triangle operation, those are going to be the elements in my fundamental quandle. And then we assign some relations to them, namely the relations which tell me which arcs are actually adjacent to which other arcs. So in this diagram, for example, arcs 1, 2, and 3 are not independent of one another because 3 is the triangle of 1 with 2. That's what we get when 1 crosses under 2, gives me 3. So I make that one of my relations. I also make all the Idempotency equivalences part of my relations as well. Once I do that, I get this ginormous structure, which not only is going to have one element for each arc in my diagram, but it's also going to have some stuff which is not actually arcs, like the first arc triangled with the fourth arc. Well, those arcs don't actually meet at a crossing. Right? So the first triangled with the fourth doesn't actually give me a different arc in the diagram. It just gives me a new element in my fundamental quandle. So it doesn't simplify, is maybe another way to think about it. But that's okay. It's all part of the same gigantic structure that we call a fundamental quandle. So this structure is a quandle because we're explicitly imposing the operations on it that define the quandle, define this crossing operation. And it has everything we could ever need to know about this knot except for the chirality inside of it. It is deducible from this fundamental quandle. The problem with the fundamental quantal, though, is it's so ginormous, right? It's such a large infinite set that it's impossible in general for us to wrap our arms around it completely, to actually write down this is the fundamental quantal of this knot. That's almost virtually always a non-starter. So the best that we can hope to do with the fundamental quantal is to interpret it in different ways, to see the fundamental quantal as a module over the ring of Laurent polynomials. That's actually what we were doing when we were studying the matrices with the t's in them a minute ago. That was one way of getting a viewpoint on the fundamental quantal. Another way would be to view the fundamental quantal as a group. We're going to do that as well. And so what I want to do to wrap things up today is to look at what it means to verify, and what I'd like to do, I guess, is to verify that we can look at the fundamental quantal in those two different ways and get some partial, almost complete but not completely complete information about the fundamental quantal of a knot. So what I want to do, so the two ways in which we're going to interpret the fundamental quantal, in other words, we're going to kind of relate it to a more familiar structure. And in doing so, we're going to lose a little bit of information such that the things that we get are not going to be complete invariants, but they're still invariants with a lot of interesting structure. On the one hand, we have a way of representing the fundamental quantal as our magic average operation applied to the elements of some ring with an identity element, where T is an invertible element of that ring. So here the prototype is, think of S as the integers mod n and T as an invertible element mod n. So it just gives us the colorability magic average. So we just want to verify that this magic average equation actually satisfies the three properties that we need for it to satisfy. The toughest one to verify, I think, is invertibility, but that's actually the thing that we just did a few minutes ago. So we want to verify all three of these. But for the invertibility part, again, interchange x with z and solve for z. So that's something you can do in either case, right? That's always going to give us a way to verify that there exists an inverse for those operations. The first property is usually pretty quick. So probably most of your effort is going to be spent verifying properties 2 and 3. Let's, for example, just look at property 3 for this, for the magic average interpretation of the quantal operation. So we need to verify the self-distributivity property, that for any elements x, y, and z, x triangle y triangled with z is equal to x triangle y triangled with x triangle z. So we just have to compute the left-hand side and the right-hand side and verify that those two things agree one with another. So for example, x triangle y triangle z is tx plus 1 minus ty triangled with z. Right? And so then that becomes t x triangle z plus 1 minus t y triangle z. And then you work out each of those trianglings also. So t times x triangle z is going to be t times tx plus 1 minus tz. And then 1 minus t times y triangle z, ty plus 1 minus t z. And so you do a bunch of algebra to work all of that out. And then work out the right-hand side also. Just verify that those two things are equal.
So for the first part, tx triangle z.
This one here.
Yeah.
Uh-huh.
So we're using the same equation from above, but switching. Well, we're using x and z instead of
Yes,
x and y.
Exactly. Right.
Okay.
Right. So this equation is just defining what it means to triangle two things.
Okay.
Right. And so anytime I'm triangling two things, I can use that template to do so.
Oh.
Right?
Okay.
So x triangle z is tx plus 1 minus tz.
Okay.
Y triangle z is ty plus 1 minus tz. Same idea. When we're defining an operation, what we're really doing is we're defining a function. Right? The function's name is triangle, and it takes two arguments, which we're calling x and y in the definition. But just like our high school algebra students struggle sometimes with f of x and the fact that x is sanctified somehow in that notation, really it's just there as a placeholder. And the x's and y's are placeholders in a similar way in this definition. Right? So for example, then when you're working out the first axiom, x triangle x equals x. So what's x triangle x going to look like according to that template?
Tx plus 1 minus t times x.
Yeah. And now you can see what's going to happen if you simplify that. X. So that's going to be the first way, and you've got some details to fill in on that one. And this, again, when we interpret the fundamental quantity using the magic average as our triangling operation, what we're getting is called the Alexander quandle, or an Alexander quandle. It's called an Alexander quandle when it's called maybe a better way to say this, it's called the coloring quandle of a knot, when the elements of my ring are actually the integers mod k. Right? If I'm asking about k colorability, then we'll take, so example, if S is Z mod K, then this is a coloring quandle. Lambda K comma T is the notation we typically use for that. So that connects us back into questions about coloring. The second way that we're going to interpret the fundamental quandle is we're going to map it over to questions about groups and group operations. So if I have a group, and a group is nothing more than a set with a binary operation that's associative, which has an identity element and which has inverses for every element. But that's as much as we know. It doesn't have to be commutative. It doesn't have to have a second operation that distributes over. It doesn't have to have anything. It just has a single operation that's associative, has inverses, and has an identity. And we define the triangle operation on group elements to be x triangle y is equal to y inverse xy. And in between these elements is the hidden group operation. So if you want to, you can put a little dot there to remind yourself that that's the group operation. But usually in group theory, we just leave out that dot and understand that juxtaposition means operation. And so we want to show that that system also meets the criteria to be a quandle. So same kind of process for the invertibility. Interchange x with z and try to solve that resulting equation for z. I actually want to do that as our example here. So if z equals x triangle y, then what is x? So that's really kind of what we're asking here. So z equals x triangle y, but that's y inverse xy. And now I'll interchange x with z and then solve for z. Y inverse z, y. And I want to solve this for z. And so this I'm using as an opportunity for us to get back into our group theory brains a little bit and think about how are we going to solve this equation for z. I want to get the z by itself. Keeping in mind, and this is the most important thing about doing algebra in groups, that our operation is not necessarily commutative, So it matters, for example, if I multiply everything in this equation on the left side by something, or whether I multiply everything in this equation on the right side by something. As long as I do the same thing on both sides, I'm still going to be doing valid algebra. So if I want to get this z by itself, what should I multiply by, and on which side should I multiply by it?
Multiply the left by y and the right by y inverse.
Yeah, so multiply everything on the left. So left multiply both sides of this equation by y. Right? And I need to left multiply it by y, because if I tried to right multiply it by y, I'm going to get a y times a y over here on this side. And that's not helping, because I can't slide that extra y past the other operations, because it's not necessarily commutative, right? So left multiply by y on both sides. That's going to give me yx on the left side, and y inverse, zy, on the right side. And y inverse, we can be sure, is equal to the identity, and so that cancels. So we're in good shape there. Yx is equal to zy. And then what's my last step to get the y by itself?
Right multiplied by y.
Awesome. Right multiplied by y inverse. And so I end up with yx y inverse is equal to z. So, okay. So we just found out that we can solve for z in this equation. And what we end up with is that where z originally was equal to y inverse xy, if I transpose and then solve, the roles of y and y inverse get traded. So it turns out, according to this calculation, that we can always invert the operation of triangling by y. And on the one hand, we found out that if x is z triangle y, then z is yxy inverse. But that's the same thing as y inverse x y inverse. What I'm trying to do here is I'm trying to make this fit the template of our definition of the triangle operation. Where now the role of the y up here is now being played by y inverse instead. And so what I really have is that my inverse operation is the same as triangling by the inverse. Which is not important. We really just needed to know that it was an invertible operation, but this specifically tells us how to invert it. Just like when we found out that, that T inverse in our magic average is how we did the negative crossing. This is that analog, right? That y inverse is how we achieve the inverse of this operation. And the other two axioms to verify, those are purely computational. This, I think, was the second one is the most subtle, because it gets at that inverse function idea. So the work for next time is to chase down the rest of those implications, to see how those all work, and when we come back, we'll get more concrete about how each of these viewpoints helps us to discover new invariants for knots. So the Alexander Quantal idea lets us discover the matrix that we were playing around with today. We saw the Alexander polynomial as the first invariant that we got out of that, but if we shrink to even smaller determinants, so rather than just crossing out one row and column, if we cross out two rows and columns and take those various determinants, we're going to get yet another invariant called the second elementary ideal, which can possibly have more power to distinguish between knots. And then the viewpoint on the right, where we interpret the fundamental quantal as a group, is going to give us a powerful knot invariant called the knot group. And we'll talk some about what the knot group is actually telling us about knots. We'll get a little bit into some, what's called algebraic topology, using a group to represent a topological property. That's really what we're doing over there. So we'll talk a little bit about how that works in our next couple of classes as well.